Hey, welcome everybody to today's webinar, Influence of Door Gap Sizes Around and Under Swinging Fire Doors, presented by Mike Van Gyn and Keith Pardo. Just some few housekeeping. Please connect your audio by using the microphone icon on your slide and selecting your speakers, and type any questions you may have throughout the presentation into the Q&A box at the bottom of your screen. We will be monitoring that throughout the day. This webinar is presented by the Fire Research Foundation's 2022 webinar series sponsors, American Wood Council, AXA XL Risk Consulting, FM Global, Reliable Automatic Sprinkler Company Incorporated, Intelligent Engineering and Consulting, and the Zurich Services Corporation. A little bit about our presenters today. We have Mike Van Gyn of QAI Labs. Mike is a fire testing expert and account manager at QAI Laboratories, where he is responsible for the fire test program development and project quality control. Mike has 40 years of conformity assessment fire testing laboratory experience. And we have Keith Pardo of Pardo Consulting. Keith is the president of Pardo Consulting, LLC. Keith's career in the swinging door industry spans more than 37 years. He provides consulting and training services regarding swinging egress and fire doors. Over the years, Keith has participated in the development of the codes and standards that affect swinging fire and egress door assemblies. Currently, he is the chair of NFPA's Fire Door and Windows Technical Committee. This webinar is being recorded on behalf of the Fire Protection Research Foundation, FPRF. This recording will become the property of FPRF and may be used by FPRF for any lawful purpose. By participating in or attending this event, you agree to be recorded and to allow FPRF to use such recording for any lawful purpose. If you do not wish to be recorded, please hang up or exit the meeting at this time. And now I will kick it off to Keith.
All right, well, thank you, Brittany, and welcome everybody. My job at the first part of this presentation is to give you context, to explain where we are, how we got to where we are, and just a little bit of the background so that when Mike presents the technical aspects of this, you'll have that frame of reference. But first, we want to thank the sponsors for this project. And primarily, the primary sponsor was ASHE, the American Society for Healthcare Engineering. They funded a great deal of the cost of the actual fire door testing that we performed during this phase of the project. Other sponsors are the Builders Hardware Manufacturers Association, the Steel Door Institute, NAM and HMMA, specifically the Hollow Metal Manufacturers Association. Both HMMA and SDI produce hollow metal or steel doors and frames, many of which are fire rated. And the Window and Door Manufacturers Association, WDMA, they represent the manufacturers of the commercial or architectural grade wood fire rated doors. And of course, NFPA and the foundation were also other sponsors. Here's a list of the people that participated in the project on behalf of the sponsors. You might recognize some names on the list here. Many of these people are also members of the NFPA 80 and 105 technical committee. So all of us have been around this subject matter for a long time. The technical panel members are these folks. And you can see some names that you might recognize here as well. And Srini, he's the one that kept us all in line. He kept us going in a straight line, so we didn't zig or zag too far. He kept us under control. So he did a great job in keeping us on task. All right. So here's where we start. Fire doors have one job. That's it. Have you ever wondered why we have fire doors in our buildings? Ever really stopped to think about why we have these doors? We have them simply because the codes require them. We have fire compartments in our buildings, and in those walls and partitions, in those barriers, we need to have fire-rated doors. The reason those doors are there is to prevent a fire from spreading. That's their one job. They do other things, obviously, right? Swinging doors do a lot of other things. But their one job is to prevent a fire from spreading. They give us time. They give us enough time to reach safety. They give us time for the fire suppression systems to do their work. They give us time. That's why they're not fireproof. They're not going to protect the building forever, but they'll do their job long enough. Some of you might be familiar with the different levels of fire ratings of our swinging doors. This is a quick list of them. The one in red, the half-hour door, it was in our codes and standards for a short period of time when you look back at the longevity of our codes. Some of the older existing buildings, you might find them out there. Today, we don't use the half-hour rated door so much, but it's a viable fire-rated door assembly because it was allowed at the time of construction. So we have to remember, it's not just about new construction going forward, it's about what's already out there in the world, what's already in place, what's already doing their one job, hopefully. So because fire doors have that one job, they need to be maintained in a constant state of readiness. It's a little bit of a different perspective than you might have heard before, right? A constant state of readiness. We don't know when there's going to be a fire or where there's going to be a fire. The codes demand in these locations there will be fire doors. The expectation is that those fire doors are properly installed. They provide the correct level of fire protection rating necessary for that area of the building, and they're properly maintained. They are able to do their one job. The basic operation of fire doors, of swinging fire doors, you can see on the screen. They have to swing easily and freely. They have to close completely and they have to latch. A swinging fire door, whether it is a self-closing door or an automatic closing door, doesn't matter which. In the end, they must close every time from any partially open position. That's how they do their one job. That door must be closed at the time of fire, closed and latched. They must be enabled to do their one job. Now, this project, this is the second phase of the research project, which the first phase started back, I think, around 2015 or 2016. And in this particular phase, we actually were able to conduct experimental full-scale fire door tests. Mike's going to explain in great detail the types of tests that we did. But we were trying to find out what if we had these gaps? How does that affect the performance of these doors? So on purpose, we chose doors that are representative of the older doors, the doors that have been out there for many years. Mike's going to talk a little bit about the difference between neutral and positive pressure in a little bit. Positive pressure fire door testing. Today, that's something we are very familiar with, but it's only been about 20 years, a little over 20 years, that we've had positive pressure fire door testing. Prior to that, all of the fire doors were tested under what's called neutral pressure testing conditions. So that's why we chose the older style doors, the older type of doors, to conduct this testing, to find out with these older doors, if they have these larger gaps, how is that likely to affect their performance? So keep that in mind. Older doors, when I talk about older doors, doors 25 years and older. Think of it that way. So we wanted to know, with the gaps, how do they affect the performance of the door assemblies themselves? In other words, will they stay in the opening? Will they remain in place? The ability of the doors to prevent a fire from spreading. It's a little bit difficult to judge sometimes because remember, we're conducting laboratory testing, but theoretically we could have a door that remains in its opening, but if the gaps are so great that it allows fire to pass under or around it, it hasn't done its one job. So we're curious to find out where that line is. And then lastly, and that last bullet point is just as important as all the others, the influence door gaps have on fire and smoke development. Again, if the fire door remains in place, but we allow too much smoke, or worse, we allow fire to spread beyond the opening, well, then that fire door has not done its one job. That's what it all comes back to. It's really what it all comes back to. When we talk about these older existing swinging fire doors, those doors that are 25 years and older, these are the older fire door tests that they were tested to and part of the building codes of those days. All 4 of these tests are neutral pressure fire door test standards. That's how they were tested. When we talk about the older model building codes, today we're all conditioned. We understand we're familiar with the International Building Code, right? It's fairly much uniform across the country these days. However, not so long ago, we had these other model building codes, and they were more regional, right? Many people forget that these original building codes even existed. But in the case of fire doors, and especially later when you think about under the context of performing safety inspections of swinging fire doors, you really have to be aware of the model building codes, at least, that were in effect as of the date of these installations. Because there's no expiration dates. There are no expiration dates on these fire doors. Think of it that way. A door from 1947 that was installed properly and properly maintained and in otherwise serviceable condition should be allowed to remain in service indefinitely. But the rules in 1947 are much different than the rules are in 2022, right? So we have to be mindful of all that. Again, we're just trying to, this project is trying to answer the question of how these older doors might perform. Another disparity we're trying to figure out is that those of you who are familiar with NFPA 80 might already be aware of this. That NFPA 80 in some cases allows for greater door gap clearance dimensions than the fire door test standards. Now remember, the fire door test standards are laboratory conditions. Some might call them a worst case scenario condition. Depends on your perspective of worst case. 80, for instance, allows a 3/4 inch gap underneath a maximum of 3/4 inch gap underneath a swinging fire door, a Chapter 6 NFPA 80 swinging fire door. The fire door test standards, today's test standards and yesterday's test standards, for single doors, that gap under the door, that dimension was limited to 3/8 of an inch. It still is today. For pairs of doors, it was 1/4 of an inch. It still is today. That's how our new doors, even today, are tested under positive pressure, as far as the gap clearances are concerned. The 80 allows larger clearances. So that was part of the curiosity, if you will, that of this project. What difference does it make? How much of a difference does it make, if any, to the performance of the doors? And because of these inspections that have been going on for a while now, since about 2007, there's been interest in raising the gap at the bottom of the door from 3/4 of an inch to, say, an inch, possibly 1.25 inches. What what would those changes do to the performance of the doors? So that's what we're going to find out when we get into talking about the details later of these tests. We tested some of the doors with a 1-inch clearance, and Mike will tell us all about it. But that's what we're trying to figure out. And as the slide says, NFPA 80, there's no documentation in the history of NFPA 80 that explains the disparity between the test standard clearance dimensions and the installation test or the installation standard requirements. Think of NFPA 80 primarily as an installation standard. That's really, it's an installation testing and maintenance, testing and inspection and maintenance standard these days. These are our current fire door test standards. NFPA 252. It includes protocols for both positive pressure testing and neutral pressure testing. And UL 10C for swinging doors is the positive pressure test that we have in our country. The note at the bottom is kind of interesting. Most people don't think about it this way. The fire door tests themselves are not concerned with the volume of smoke that passes around or under a door. We have NFPA 105, right? Some of you understand when you hear the term UL 1784, an air leakage test. Those are measurements of the airflow around and under a door at elevated temperatures, at ambient and elevated temperatures. Anyway, the fire door test standards themselves don't care about smoke. So that's another aspect that we're trying to figure out with this phase of the project. So again, we sought to learn how these larger door gaps might affect the performance of the doors and their ability to do their one job. Now, I want you to keep this in mind. We conducted, I think it was 17 tests, Mike will tell us for sure, how many different assemblies we tested. But in all the tests that we conducted, it is an extremely small sampling and not representative of the greater body of the swinging fire door constructions that are out there. So keep that in mind. This is a very, very small sampling. Now, what is critical to know about this, the note at the bottom of the slide tells us that we use products that already had passed fire door testing. These were products of known quality. They've already passed testing by their respective manufacturers. We installed them in non-typical, non-standard applications by changing the door gaps at the bottom and along the vertical and top edges. We introduced these different conditions. The idea is, okay, let's take a product that we know and see what happens when we change these details. When you think about the world of hollow metal doors or steel doors, commercial steel doors, swinging doors, these are all the different types of constructions that we have, the different types of cores. They can be made out of 20, 18, 16, and 14 gauge steel face sheets. So there are a lot of different combinations of core and edge construction and face construction, and each manufacturer builds their products differently. The end result appears to be the same, but internally they're different. When we talk about wood fire rated doors, there's actually very little wood in wood fire doors these days. These are some of the cores. But even when we talk about mineral board core, which is that gypsum-like thick core, there are different categories, different formulas of that gypsum product, of that mineral board core product. Some have more capabilities than others. So again, you can see this, it would be very difficult to conduct experimental fire door testing of all possible combinations of doors. We just can't do it. So keep that in mind. So I'm just about done. I'm one word of caution, warning, viewer discretion is advised. Again, keep everything in context. Mike's going to share the information that we found, and you can see where it takes us from there. All right, I'm done. I'm going to turn this over to Mike.
Thank you, Keith. Before I get into the test results, I just want to add a little bit to what Keith was saying. You'll see references to positive pressure testing versus neutral pressure testing. And, this happened in the transition between the 1997 Uniform Building Code and the International Building Code around 2000. So when we do the actual fire test, the standard requires us to achieve the positive pressure within 5 minutes. So the way we do this is we slowly close the furnace damper to restrict the exhaust. And this bottles up the hot gases in the furnace. And as we gradually lower the damper, the transition line between positive pressure and neutral pressure gradually lowers from the top of the door down to the latch level. So at 5 minutes into the test, we have our positive pressure achieved at the latch level. So what this means is that at any elevation below the latch level, we still retain a negative pressure, so any air will go into the furnace. And at any point above the latch level, hot gases will be trying to get out. So they'll tend to come out between the edges of the door. So as you go gradually higher above the latch level, that pressure increases. And as you go down below the latch level, the neutral pressure or negative pressure increases. So you have this balance of cold air going in below latch level and hot gases trying to get out above the latch level. The other point I want to mention is that the report focuses a lot on the difference between a 3/4 inch sill gap and a 1 inch sill gap. But also the door edge and top gaps were set at the maximum allowed by NFPA 80, not as per the test method NFPA 252. So in a regular 252 fire test, the gap's allowed to be 1/8 of an inch, but can be less by a 1/16. Whereas in NFPA 80, those gaps are 1/8 for wood doors and 3/16 for steel. So in this test series, the side gaps and the top gaps all were set at the maximum allowed by NFPA 80. In conventional door testing, it's rare that you would have the maximum gap in all locations. You may have a larger gap on one side, a smaller on the other, and so on. So even though the report focuses on sill gaps, keep in mind that all of the gaps were set at the maximum permitted by NFPA 80. So I work for QI Laboratories. We did the test series at the Burnaby, BC laboratory just outside of Vancouver. The first test was conducted on July 23rd, 2020, and we finished in July 12th, 2021. The reason for the time frame, the original intent was that the technical panel would come out to the lab and personally witness the test series. And obviously with COVID-19, this was no longer a possibility. So initially, we thought that COVID-19 would be over in a few months, so we just postponed the program. By the time July came around, we realized that this was not going to happen. So we provided a remote viewing option using stationary web cameras and a mobile camera. So the technical panel was able to observe the tests remotely, and they're able to see the lab computer, which displays the data and the time temperature curve and the pressures, etc. And we're able to communicate directly with the lab using the two-way voice communication using the Google Meets program. So this was, an experiment in its own right, but it worked fairly well. And we continued to do that through the entire test series. So the first series was the proposed initial program of 9 fire tests. But the results of the 9 tests showed that there was some more information that was needed. So the test series was expanded by adding 4 more tests. In all of these tests, the clearances of NFPA 252 were not used. And the sill clearances were set at 3/4 inches, which is the maximum allowed currently by NFPA 80, and also at the increased gap of 1 inch, so that we could evaluate the difference between the 3/4 inch and the 1 inch gap on identical test assemblies. In the second series, the thought was, well, what would happen if we did the same test, but with the 1/4 inch gap that's required by NFPA 252? So that's a comparison. And all of the tests except for 2 in the second series were conducted under the positive pressure test conditions. In the second series, we did add a frame mounted into gasket material, which is typical in a positive pressure assembly, to see what the difference was with that. So under the fire test conditions, the acceptance criteria are very specifically specified. So I want to go through those because that's what determines whether the test assembly meets the acceptance criteria or does not meet acceptance criteria. So we did a host stream test on all of the assemblies. The 20-minute doors do not require a host stream test in the USA, but we did conduct one anyway. So per NFPA 252, the first thing is the fire door assembly shall remain in the test wall opening throughout the fire and host stream test. There are specific allowances of flaming. In the first 30 minutes of the test, it's very restrictive. A flame has to be less than 6 inches long, and the duration cannot be more than 10 seconds at a time. After 30 minutes, it's a little bit relaxed. So you're allowed intermittent flaming, again with a 6-inch flame length limitation and a 5-minute time limitation. So no more than 5 minutes for each flaming event. For doors that are greater than 45 minutes duration, you're allowed to have flaming that exceeds the 6-inch length only in the last 50 minutes of the test, but also provided that the flames are contained to within 1.5 inches from the vertical edges and 3 inches from the top edges. So when you're running the fire test, you have to estimate or measure the length of the flames and time the duration to determine whether or not you meet the acceptance criteria for flaming. We go to the next slide. Next slide, please. So there's a criteria for separation and movement of the door edges. So this is dealing with if a door warps. For single swing doors, the door edge movement from the original position adjacent to the frame shall not exceed 1 3/4. So that is the depth of the frame stop during the fire test, or 2 5/8 during the host stream test. For door swinging in pairs, the meeting edges shall not move from the original position perpendicular to the plane of the doors more than 3/4 of an inch from an adjacent door edge. So if the two leaves separate from each other, they can only move degree of the thickness of the doors themselves. For pairs without an astragal, meeting edge separation, so moving apart from each other, shall not exceed 3/8 of an inch. Now, the initial clearance between the leaves of the pairs for this test series was 3/16. So the initial clearance was already half of that. So the allowable movement was basically doubling the original clearance. Single swing doors shall not separate from the door frame by more than 1/2 inch at the latch location. So if it separated more than 1/2 inch and you had a 1/2 inch latch throw, the door would then become unlatched and it would be able to swing open. But regardless of the latch throw, your maximum permitted separation is 1/2 inch at the latch location. Okay, for what we tested, the door frames in all cases were 16 gauge pressed steel, fully welded frames installed in concrete masonry unit block walls. The pairs of doors were installed in a double egress configuration frame. So all the pairs were double egress. There were no standard pairs. The steel doors were 18 gauge skins, 90-minute fire rated, labeled flush lock seam type polymetal doors with a paper honeycomb core. Each leaf 4x70. For wood doors, they were wood edge, 20-minute rated particle board core, solid core flush doors. Each leaf was 4x70. And these are what we called category B doors. So these are essentially traditional doors tested under neutral pressure conditions with no intumescent in the door edges. There is one exception though. In order to meet the listing, the pairs of wood doors did have an intumescent in the meeting edges of the pairs. So under positive pressure test conditions where you have hot gases that are trying to escape through the door gap in the upper part with the code change in 2000, one of the solutions to the effect of that erosion from hot gases was the installation of intumescent either in a door edge as a concealed intumescent or added to the frame. So if the door contains the intumescent and it's hidden, it's considered a category A door. And if the intumescent is added after, it's a category B. So category B is a traditional door that doesn't contain anything different in the door edges. For the composite doors, which are 90-minute rated mineral core type doors, they're also flush doors. All the doors were 4x70 nominal size, each leaf. Also category B, there were no intumescent materials used in the composite 90-minute doors. All of the doors and frames were listed products that bore the agency labels on them. For the hardware, the hinges were standard on all the doors, 5 inches by 4.5 by 0.190 thickness, full mortise, 5-knuckle ball bearing steel hinges. So standard commercial grade conforming to NFPA 80 hinges. The latch was a commercial grade mortise lock passage type using lever type handles. Very standard hardware. For the pairs, same hinges. For the latches though, they used a vertical rod type, top rod only, so less bottom rod, fire exit hardware with lever trim on the pull side. So because all of the pairs were double egress design, the vertical rod hardware would be, the push bar would be on one side for one door and on the other side for the other door. Because of the top rod only configuration, the listing required an auxiliary fire latch or thermal pin to be installed near the bottom of the meeting edges. And this would be to latch the pairs together because there's no latching to the floor. So these auxiliary fire latches or firing pins were installed at 6 inches from the bottom of the door for all the double egress pairs tested. There were no astragal used on the pairs, so they're just plain edged doors. The single swing doors were tested side by side, with the only difference being the sill gap of 3/4 inch and 1 inch, so we could compare the results for the single swing doors at the same time. So this is a photo of the actual test installation for the wood door test. The door on the right has a slightly larger sill gap, 1 inch in this particular case. As with all door testing, these doors are oriented to open towards the fire. In the case of the double egress pairs, it doesn't matter because you always have one door opening into the fire and one door opening out. Because of the size of the opening versus the size of the furnace, the pair assemblies were tested in separate tests, with one test having the 3/4 inch gap under the sill and the next test having the 1 inch gap on the sill. So this photo shows the test configuration for double egress pair wood door. So this is a description of the test series for the first 9 tests. So essentially we would have one test of 2 single swing doors of a given type, and then a second test of a pair with 3/4 inch sill gap, and a third test of a pair with 1 inch gap for 20-minute wood doors, 90-minute composite doors, and 90-minute rated steel doors. So 3 types of doors, 3 test configuration is 9 tests. Everything's the same except for the 3/4 inch versus 1 inch sill gap. So we didn't do the doors in order. We've listed them in order, but the dates are different for a variety of different reasons. For the second series, the second series was determined by the test panel, the technical panel, as a result of the results of the first series. So this is exploring a few additional details. So test 2.1, we added the retrofit door edge intumescent to the frame, which is typical for positive pressure assemblies. So this is a duplicate test, but with a retrofit intumescent added for the 2 single swing doors, one with a 3/4 inch sill gap and one with the 1 inch sill gap. The second one was also single swing doors, composite doors, so the 90-minute mineral core doors, no edge intumescent installed, but tested under the old style neutral test pressure. And that was tested with a 3/4 inch sill gap. So this test was looking at, what would happen if you did this in 1997 and you just changed the sill gap from the required 1/4 inch to 3/4 inches. The third one was a double egress pair, 1 inch sill gap, neutral pressure, 90-minute rated. So a duplicate of the previous one, but with the 1 inch sill gap. And the final one was testing the doors, composite doors again, 90-minute rated mineral core with a 1/4 inch sill gap. So testing the same assembly, but as per the requirements, sill gap requirements of NEFPA 252. So the second series looked at things a little bit more depth. So we'll get into the actual test results. As you can see, if you go through the list, the steel doors, the first test of steel doors, double egress pair, 3/4 inch gap, sill gap, it met the acceptance criteria of both the fire and the hose stream test. For all of the other tests conducted in the first series, there was some technical issue that resulted in the test not meeting the acceptance criteria fully. So on the steel doors, they all passed the hose stream test. However, only the single swing doors completely met the acceptance, or sorry, only the 3/4 inch sill double egress met the acceptance criteria fully. The single swing doors did not meet acceptance criteria fully, neither did the double egress with a 1 inch sill gap. On the wood doors, the 20-minute rated wood doors, none of the tests met the acceptance criteria of either the fire test or the hose stream test. And the same in the case of the mineral core composite doors, none of those tests fully met the acceptance criteria. So some were better than others, but when you go to the exact requirements of the test method for both flaming and separation, etc., they did not fully meet the acceptance criteria. For the second series, the performance of the second series was different in many cases. However, to our surprise, in many ways, none of these tests fully met the acceptance criteria as well, of either the hose stream test or the fire test. So look at the steel door tests. The steel door tests, I would say, generally performed fairly well. So the primary problem on the single swing doors was we did see some flaming in the early part of the test. So in both the 3/4 inch, 1 inch gap, sill gap tests, so these are side-by-side comparisons. We had flaming in both cases, but this problem only lasted 10 minutes. After the 10 minutes where the flaming was out, there was no further issues with the doors. The issue here is that flaming is allowed in the first 30 minutes, but the duration is very limited. So we have a 30-second maximum duration, but we had flaming for 2 minutes in one case and for almost 5 minutes in the second. So although flaming is allowed, flaming is not permitted for the duration that occurred in those tests. The 3/4 inch double egress pair assembly met the acceptance criteria, and there was no flaming that occurred. The double egress pair, same test with the 1 inch sill clearance, we had excessive separation of the meeting edges. And this is due to the distortion of the doors due to thermal expansion. And this occurred at 50 minutes. So this is where the meeting edges are only allowed to separate 3/8 of an inch. So the separation at 50 minutes exceeded the allowable 3/8 of an inch. Here's a photo of the steel door tests where you can see the flaming that occurred on the single swing door. So in this case, the pressure is positive, so you can see that there is smoke that is coming out between the door and the frame. on the right side door. So at any point below the latch, air would be going in. On the left side door, you can see that these gases that you see coming out on the right have actually ignited, and that's causing the flaming that you see. For the steel door with the 1-inch sill gap, the maximum gap occurred right where the hardware is located. So you can see that the doors are tight at the top and fairly tight at the bottom, and the gap is the largest at the center. So these doors are bowing inward towards the furnace, and that bowing is causing the gap that you see in the middle. So the gap is only allowed to be 3/8 of an inch when it started out at 3/16. So those doors, that gap is opened up more than 3/16 from its original point. So the gap is not huge, but it's beyond the 1/2, the 3/8 inch that's allowed by the test method. Next slide. For the wood door tests, in this case, the primary issue here was flaming, and wood doors are, the wood edges are quite vulnerable to the positive pressure test scenario, because the hot gases that are trying to escape from the furnace by coming out between the door edges and along the top tend to erode. The wood edges tend to erode from these hot gases, and this causes flaming, particularly in the positive pressure zone. So the flaming occurred at different times, but once it started, it was continuous basically till the end of the test in most cases. The other problem is that the erosion of the door edges is a problem for the hose stream test, because the force of the hose stream will push the door up against the frame stop. And if the edges are gone, then there's nothing to stop the door from being pushed through the opening, and we did see this happen. If the doors, okay, here's a photo of this is the very typical result of the wood doors under the positive pressure conditions. You can see the flaming is quite severe. It's worst at the top where the positive pressure is the greatest, and it's less as you come down towards the latch. On the door on the left, you can see that there's burning on the face of the door skin, so that the flaming has traveled a bit across the door face. For the pairs, very similar, a type of event happening. In these doors, there is intumescent at the meeting edges, but only at the meeting edges. You can see that the meeting edges are quite tight, and we don't see any flaming along the meeting edges. For the composite 90-minute mineral core doors, flaming was a big problem as well. Once again, these doors still have some wood around on the edges, and this wood would tend to erode when they're in the positive pressure zone. So flaming, we did not see flaming on the 1-inch sill single swing, but we did on 3/4 inch. We don't really know why there's a difference. But we did also have burn-through openings on the mineral core doors. These burn-through tended to be, we'll see in a photo, but they tend to be between the core and the stiles. In the case of the 1-inch pairs, we did have we had a problem with the test installation on this test, and we stopped the test at 60 minutes. We had an issue with the header where we weren't able to maintain the pressure in the test. So, this test was essentially discounted beyond the 43-minute mark. In the case of the gap, can we go back one slide, please? Okay, thanks. We'll go next slide. So in the case of the flaming, on the single swing doors, we did have burn through between the core and the stiles. Not in all cases. We had problems with the meeting edge door gaps. This is the second series. We had problems with the meeting edge gaps on the double egress pairs. And this happened irrespective of the clearance underneath the doors, we still had erosion of the meeting edge gaps. The second series tests generally still did perform a bit better than the first series, but we were surprised that we still had these issues in the test results. The next slide. These are the mineral core doors at the end of the test. So you can see there's a lot of curvature of the doors. There's a lot of what we call bowing, where the door is bowing towards the furnace. These doors, because of the edge erosion, they were dislodged during the hose stream test. Next slide. This meeting edge gap is a burn through. So there are wood edges. There is some wood material along those edges, and this wood material burned away. And this is in the negative pressure zone at the bottom of the doors. And because the material has gone, that's where you measure your maximum gap. Where there's no burn through, you can see that the meeting edges are actually touching each other. So this was the common issue that we saw in the mineral core door testing. And because of the edge erosion, that becomes a problem for the hose stream test. So this is the same test where you can see the burn through at the bottom that we were looking at as a close-up. You can also see that the door on the right has dropped. So the bottom edge of the door is not in line with the bottom edge of the door on the left side. So the door has tipped. And the reason for this can be seen on the top right, where the hinge that's holding the door in, there's a failure there between what appears to be the stile material and the core. So if the door is intact structurally, it would not be able to drop like that. So when we look at what the sill gap does in terms of the cross-sectional area, now keeping in mind that in the sill gap is in the negative pressure zone, so air is going to go in at any location below the latch, and the maximum negative pressure would be at the bottom of the door, so the maximum amount of air would be going through underneath the doors. So when we look at what NFPA 252 tells us to do during a normal fire test, and what was happening with the increased sill gap, the cross-sectional area increases by 240 to 320%. And if we compare that for single swing doors, if we look at pairs of doors where the standard requires a 1/4 inch gap, and we're now moving to a 3/4 or 1 inch gap, that cross-sectional area increases by 400 and 533%. So you've got 4 times the cross-sectional, 5 times the cross-sectional area. What that does is it lets a lot more air enter the furnace. Now, when you control the furnace to follow the time temperature curve, essentially you're controlling the fuel input. So there's very little that can be done to change the amount of combustion air. So generally speaking, the combustion air is controlled before you start the test. And then after that, you control the furnace by changing the fuel input. So if you're adding a lot more air into the furnace, you're diluting the heat in the furnace, and you have to compensate for that by adding more fuel to maintain the required time temperature curve. So doing that also increases the flow rate through the furnace. So what we're seeing in a lot of cases in the testing, when you're comparing the standard test gap and the test, the NFPA 80 test gaps and increasing it to 1 inch, is we're really seeing what happens when you add all of this air into a standard test furnace scenario. One of the things that we did is we used a small vane anemometer and kind of a funnel to actually measure the airflow that was moving through under the door. Now, this is not an exact measurement, it's just for comparison purposes. So we could say, well, what is the actual airflow? Now, one of the things that we did notice is that between the left side and the right side door, when you're doing pairs, on one case, you've got the hardware on the fire side, and the other case, you've got the panic bar and the hardware on the non-fire side. And on the fire side, these components are made out of aluminum, and they would tend to fall off the door and rest on the sill, and in some cases they would melt. So the debris from the hardware tended to slow down the airflow a little bit on one of the leaves versus the other. But what we see in our measurements is that the airflow on the 1 inch sill gap was generally greater than the airflow we measured with 3/4 inch sill gap. So we would expect that because of the additional cross-sectional area, but it was nice to get that actual data that shows how much that airflow really changed. In the case of the 1/4 inch sill gap, we could not get a measurement because we had to have a flow of greater than 50 feet per minute to register on the meter. So it's not really accurate. We were well below that, so we couldn't get a reading. So that shows that in conventional testing, the airflow under the doors, particularly for pairs, is significantly restricted. So as I mentioned, this airflow is a problem. It cools the furnace. It results in the operator having to add more fuel. This increases the flow rate. And when you increase the airflow and you increase the fuel, you have increasing the convective heat transfer to the sample. So an analogy to this is is a convection oven where you're cooking at the same temperature, but it cooks faster because the air is moving around in the oven. So there's a convective heat transfer change when this flow rate increases. The other thing that happens in the case particularly of wood doors is that you're increasing the amount of available oxygen. So it increases the rate of combustion of combustible materials. So when you restrict the air going in, a lot of the oxygen is used by the burners, and it tends to slow down the rate of burning of the door skins and the door cores in the case of wood doors. So when you greatly increase the amount of oxygen, you'll see more intense fire. And we did observe this in the testing. So in the case of comparing positive pressure on doors originally tested under negative or neutral pressure, we have the hot gases passing around the door edges that can erode the edges and increase gaps and also cause flaming. The typical solution to that since 1997 has been to add an intumescent material. So intumescent materials expand when they see heat. They basically operate based on containing water, which turns to steam in one form or another, so that they expand and they seal up the gaps. So in the case of where we don't have that intumescent material, there's nothing that is present that can compensate for the gap. The other thing is that the intumescent materials that are currently in use were designed to function under the test conditions of NFPA 252. We're using the gaps specified in 252, which around the sides and top were less than what we used in this program. So the intumescent material will not be as effective. So in the test where we used intumescent, it wouldn't be as effective because it wasn't really designed necessarily to deal with increased initial gaps. So at the end of the day, this test program revealed that the edge and sill gap dimensions have a fairly significant effect on the fired hose stream test performance. Not only when tested to positive, but also when tested to the neutral furnace pressure test conditions. In the case of the steel doors, we can see that the effect was fairly minimal. We did see that flaming that we wouldn't have expected, but generally those doors performed quite well. And they passed the hose stream test in all cases. We had a slight excessive gap between the meeting edges in one case, and we had flaming on another. But in terms of comparing, they were reasonably close. In the case of the mineral composite doors, the effect was much more significant, and we didn't have an assembly that fully met the acceptance criteria of the fire and hose stream tests. Our conclusion from that is that a main reason for that would be the increasing sill gap clearance. when the mineral core doors were tested with the standard gap clearance, they still didn't meet the criteria, but the performance was improved. In the case of the wood doors, the effect was significant as well, and we didn't meet the acceptance criteria of the fire and the hole stream test. So we conclude that increasing the sill gap decreases the fire test performance of the 20-minute rated doors. There's a lot more work that really needs to be done to really fully evaluate the effect of not only the edge gaps, but also the sill gaps. One of the things that we were thinking is that we didn't really have a clear baseline test, even though these products had met the requirements of the test standard when tested to NFPA 252. We didn't have a direct comparison of this exact configuration with these, not only the base clearance correct at NFPA 252 requirements, but do this exact assembly in accordance with 252, and then with the change in the sill gap. So without the baseline test of the exact configuration, it's harder to make direct conclusions on the effects. The effect of the intumescent, particularly on wood doors under positive pressure conditions, is significant. So if we move this to doors that were made after the year 2000, where intumescent would be used, how would the change in gaps affect that? Same thing if you used retrofit intumescent systems. How would that work? So there's still a lot of unanswered questions. You know, did we see failures just because of the difference between positive pressure, neutral pressure, or was it really due to the change in the sill gap? And then a final thing might be, well, if a 3/4 inch sill gap is a problem, then where does that, if you compare the NFPA 252 requirement, say of 1/4 inch, at what point does the problem begin? Does it start at 1/2 inch or 3/4 and so on? So there's still a lot of work that needs to be done to fully understand exactly what happened and why it happened, and how it affects all of the doors in the marketplace rather than just, the category B types that we used in this program. Another topic would be what happens with regard to containing fire smoke and gases. We were only looking at fire test performance and the strict criteria of the fire test. That's only really part of the full performance of a fire door. So a real fire is very different from the standard test conditions of a test furnace. In a real fire, you don't have an operator, changing the fuel input. So one way of addressing this would be through computer modeling of real rooms and spaces and how the gap would affect the models. And modeling can be done over a variety of different clearances and conditions. So it can greatly expand the knowledge base that we're looking at. So the full test report is available on the NFPA.org Foundation website.
Thanks, Mike. Before I get into my final slides here, there are some questions in the Q&A. If you and Keith want to take a look and answer any of those live, feel free.
Keith and Mike, if one of you want to take that question, there is a question about clarifying or understanding of the category B door. So the question is, it was my understanding that category B doors require labeled edge seals or gaskets installed on either the door or the frame in order to achieve their listed rating, and that only category A doors can be installed as delivered from the factory without edge seals or gaskets. Could you clarify the category B doors from the context of this experiments conducted?
Yes, that is correct. The category B door, if installed in a positive pressure location, does require the addition of a listed intumescent that's listed for the door and frame type of the site. So in this case, we used a category B door under a positive pressure test condition, but without the addition of the intumescent, except in one case in the second series.
Mm-hmm. And there is a question, I think probably, Keith, you can respond to this. This is in relation to a previously provided response by you. You provided the response about the smoke leakage rated doors are not fire rated. It depends on occupancy. I think the follow-up question is, weren't smoke barrier partition doors 30 minutes?
Well, as far as the 30-minute fire door, that goes back to what the building codes call for different locations. And originally they probably were something in a smoke barrier type application. I without looking up the actual code, I can't tell you for sure where they were. Mm-hmm. But as far as a smoke door rating, fire doors have an hourly rating, right? 20 minutes through 3 hours, the different levels of fire protection rating. But a smoke door assembly has set aside, there are non-fire rated smoke door assemblies, smoke leakage rated doors, smoke and draft control doors under the IBC standards. The smoke door itself has no hourly rating. So it's beyond the subject of this test or this webinar, but the UL 1784 test is a 30-minute test. There are 4 iterations of the test, and it's a 30-minute test each cycle of it. But so I'm not sure of the context of the question.
Mike, probably the next question is, you can take the next question, which is about explaining the time temperature curve used for the experiments.
We used the standard time temperature curve specified in NFPA 252 for all of the tests.
Mm-hmm. And there is a question, again, related to the test, experimental test observations. I believe this might have been related to the second series test. What is the reason that 3/4 of an inch test conditions flaming was observed, probably, and observed and an issue, and in 1 inch test, no flaming occurred? I think this may be relating to that test slide number 50, probably, not sure, but
I think it's probably, my guess would be the steel door tests, and that's a good question. We don't really know. Mm-hmm. We don't know whether it was just an anomaly, or we did not come up, we're not able to determine a clear reason for the difference. You know, in theory, you would think the 1 inch would have flaming and not the 3/4, but we don't really know.
Yeah. I'll just add here, Mike, if this is this question is related to that observation where we mentioned the 1-inch experimental testing, that it showed a flaming only briefly for 1 minute, I believe. So that's kind of the observation I believe we provided. So again, we don't know the exact reason for that.
Correct. Yeah, we're not sure. I mean, there's a lot of things that happen that we can't clearly explain.
Mm-hmm. There is a question about how many scenarios did we run for each of these tests. I mean, the answer is we were not able to repeat each of these tests multiple times. So only one testing was conducted. I don't know if you want.
Yes, one trial of each configuration.
Mm-hmm.
So, one trial of single swing doors with both 1 3/4 and 1-inch gaps, one trial of double egress pair with 3/4 inch gap, one trial of double egress pair with 1-inch gap for each of the 3 door types.
Mm-hmm.
Srini, I'll answer the question about from Lyric about the door gap issues.
Sure, please. Yeah.
So there are products in the marketplace today that are designed and tested to specifically mitigate excessive clearances under the doors, at the tops of the doors, at the vertical edges, and at the meeting styles of pairs of doors. Typical weather stripping, even though it may be so-called fire rated, isn't sufficient. Some of these solutions that are out there require the application of intumescent material, even though it's not necessarily a positive pressure application. Let's remember, our older doors weren't tested under positive pressure, but if they have these larger gaps, one of the ways to resolve those gaps, they don't correct them, they just mitigate them, is to apply some type of an intumescent material. And there are all different types of intumescent materials, so you have to even be careful with that. If you put too much intumescent material in the gap, you can actually break the door. You can exert so much pressure on the door, depending on the type of intumescent, that you cause more damage than you solve. So you have to make sure you match the solution to the application. So the typical door sweep is not fire rated, is not designed rather to mitigate the clearance at the bottom of the door. Typical weather stripping is not designed to mitigate clearances. You gotta use the right stuff.
Mm-hmm. Keith, I'm not sure if you want to take the next question as well. There is a question about the doors that are tested to, if the doors are tested to NFPA 252 or UL 10C and they pass the testing, do these doors then go to the Canadian standard, I believe? Or
I could answer.
Yeah, I think it's a better question for Mike. Yeah.
All right. I can answer that. Yeah. The answer is no. Even though positive pressure testing is considered generally to be a worst case, the ULC S104 test method is a neutral pressure test method. There are differences in the acceptance criteria. S104 does not permit any flaming in the first 30 minutes. So the answer is the product does have to be specifically listed for S104 to be eligible for sale in Canada. Also in Canada, a hose stream test is required for 20-minute doors, whereas in the US, a hose stream test is optional. So no, they're not automatically okay for Canada.
Mm-hmm. And I think that there is one last question here, which is about gap gauge requirements.
We don't use gap gauges in testing. We actually, if we see excessive gap, we measure it. You can use a gap gauge, for example, for the meeting edge gap, the maximum 3/8 of an inch. You could use a 3/8 inch rod to test for whether or not it will pass through an opening. But generally, we just measure it.
Thank you, Mike. I think that's all the questions we have from the participants in the Q&A window. We appreciate you and Keith providing this webinar. I'll let Brittany to provide some closing remarks and instructions to the participants.
Thank you, guys. Do you mind going back one? Thank you so much. So if you have any other questions or comments, please email us at custserve@nfpa.org. For more information on NFPA's upcoming webinars, you can visit nfpa.org/webinars. A recording of this webinar will be made available. You'll all receive an email notification once that has been posted. And next slide, please. And on behalf of the National Fire Protection Association, Fire Protection Research Foundation, Mike and Keith and myself, thank you for joining us today.
You're welcome. Thanks.
Thank you all.